Just give me a second.
This phone is.
Okay. Good evening, one and all. First of all, I would like to welcome our today's speaker, Professor Raghavan Rangarajan, Professor from Ahmedabad University. And also I welcome our Sunday class students, Satyasar students, and also the participants. Good evening to one and all. This is the 5th lecture in his professor's SVM Satyanarayana online memo lecture series. Last 1 year, we have organized 3 lectures. And this year, in the month of May, we had one other lecture 4. The main purpose of organizing this lecture series is to spread Satyasar's commitment and dedication to physics and how he dedicated his life to promote physics teaching to southern part of India. And also we want to continue his legacy and the dedication and commitment. And we want to connect to the students and physics educators and teachers. And also we want to reach to national level audience. So this is the purpose that we have been doing this online memorial lecture series. And the first 4 lecture series, lecture 1 is given by Professor Tibaktar in the title of The Enigma of Entropy last year. And the second lecture is given by Professor Sunil Mukhi, Remarkable Outcomes of Mathematical Physics, the title. And third lecture series is given by Professor Muhammad Sajjad from Aligarh University, the title of Exact and Approximate Conservation Laws in Particle Physics. And the fourth lecture is given by Professor Shivakumar from Kriya University, the title of Quantum Computation, the Next Revolution in the Computation. And today's lecture given by Professor Raghavan Rangarajan, the title of The Cosmology, the Story of Our Universe. In fact, this title itself is a very, very attractive, and from school kids to college level, so many we have been talking about dark matter, dark energy, and the Big Bang. It's a kind of very fancy word nowadays, and even small kids, primary school kids are talking about these words. And there are so many misconceptions or wrong informations and right information. So we have to design properly. And we have a very right expert with us, and Professor Raghavan Rangarajan. So before we go to the next level, I invite our Dr. Kamal to play a short biography of our Professor Satyanarayana. So after that, we will give an introduction to our professor, then he will start.
But the audio is not coming. Is it for me alone or for everybody?
For me also, it's not coming.
Audio is not clear, I think. I could not even hear the voice.
Let me try again. Fine.
Yes, sir.
But if it is satisfying only 1, 2 and 3, then that is called a monoid. These are just names for, they exist, so I am writing. And if it satisfies 1, 2, 3 and 4, it's called a group. And if you may want to call it as a 5, if it satisfies 1, 2, 3, 4 and 5, it's called an abelian group. Learning science is not about answering a question, but it is a training to question the answers. I believe that we must judge the progress of a student not on the basis of answers that he writes in the examination, but only on the basis of questions that he asks in the class. Because the ability of questioning gives us a window to judge the understanding ability of the student. So I think, in my opinion, the first and important aspect of teaching is to make them ask questions. Now, this is a very, very tough task. We have a group of heterogeneous people with different backgrounds, different knowledge initial states, and we cannot easily make everyone to come out in open and ask questions. There will be a lot of inhibitions, there will be fear, there will be a doubt that others will ridicule, all these problems will be there. But we have to deal with all of them, we have to live with all of them, and yet make some progress in terms of training them to ask questions. This is the only way to really judge whether someone is making a progress or not. Second important thing is, how best you teach does not depend on you alone. It depends on you as well as the given set of students. So your teaching should be a function of the group who is attending. Suppose I learnt group theory. I teach everywhere in the same fashion, but the audience in one place may be different from the audience in another place. So your teaching, the content, the method of presenting, and the problems that you choose, the way you present it, everything has to be a function of the set of students or the audience whom you are addressing. So if the audience are ready to receive, then only they will receive. How much ever clear presentation that you make, if the audience have no readiness, then it all goes waste. Now, for that purpose, what we have to do is, you have to do an initial exercise of making the audience ready for what you have to teach. Okay, so how to make audience ready is another technical aspect which we will discuss. So you have to have a readiness. If you are not ready to receive, you will not receive.
Yeah, over to you, Joseph.
Yeah. Thank you, Dr. Kamal, for his biography video. So now I would like to introduce our today's speaker, Dr. Raghavan Rangarajan is a professor of physics and dean of the School of Arts and Sciences at Ahmedabad University. Prior to that, he was an faculty of the Theoretical Physics Division at the Physics Research Laboratory, Ahmedabad, for 2 decades. Dr. Rangarajan obtained his bachelor's degree at Princeton University and PhD at the University of California at Santa Barbara. His areas of research are cosmology and particle physics, and he works on the process that happened in the very early universe in the first microsecond after the Big Bang. This is a really short introduction. Of course, there is also one more connection. So our today's speaker, Raghavan Rangarajan, is a close associate of our Professor Satyanarayana. In fact, both of them conducted several programs, several PTTs together. So really, we honored you, sir, and over to you.
Thank you so much, Joseph and Dr. Kamal, and thanks to all of you for giving me this opportunity to give this talk. Professor Satyanarayana, or Satya as we all knew him, was a close associate. For many years, we conducted something known as PTTS, Physics Training and Talent Search, which was a summer program where we had for 3 weeks students from different parts of India coming together, where we taught them physics in a very interactive way, in a way that made them think about physics, both in terms of theoretical physics courses, which involve problem solving, as well as experimental physics courses, which again involve problem solving, and which required students to think about how to design an experiment to answer a question. Satya was one of the national coordinators of that program and also taught in it practically every time that we had it. Sometimes it was not even during the summer, but it was in other times of the year. But Satya was always involved in the planning of the program and, as I said, also delivering lectures as part of the course. He was an extremely personable person. You could see he had immense affection for all of his students and a huge sense of responsibility towards them. He, as one of the quotes mentioned, he gave his best to his students. And the legacy is that today across India, there are so many people, so many physicists who have been, in their earlier years, influenced by Satya. There are others who may have chosen not to continue in physics, but even there, Satya's touch would be there, because I know that he mentored so many students, talked to them not just about physics, but about other issues that were happening in their lives, and provided them with support so that they could continue doing whatever they were best at. So this talk today is a tribute to Professor Satyanarayana, and I feel extremely fortunate to be given this opportunity to make this offering to him. Wherever you are, Satya, rest in peace. Your legacy shines on and will continue to shine on for a very, very, very long time. Today, what I want to talk to all of you and share with you is about cosmology, which is the branch of physics which deals with the study of the universe. And give me a few seconds while I share my screen. Joseph, can you confirm that
Yes, sir. Yes, sir. Yeah. Yes, sir. Yes, sir. We're able to see you.
in full screen mode? Yeah.
Yes.
Okay, thanks. So as Joseph mentioned, I'm a professor at Ahmedabad University, and I work in cosmology. Cosmology is the branch of physics that deals with the study of the universe, the current status of the universe, as well as its past and its future. So what do we know about the universe today? If you look out into the night sky and you use various instruments like telescopes, both ground-based and satellite-based, what you will notice is that the universe has a lot of galaxies which are made up of stars, and these galaxies are grouped together in clusters. superclusters with empty spaces or voids in between. What we do in cosmology is to first make these observations and then use our understanding of general relativity to understand the past history of our universe and the future evolution of our universe. Now, in a sense, cosmology is a very old science because since time immemorial, people have been looking out at the night sky and asking questions like, how old is the universe? Has it existed forever or does it have a beginning? Will it exist forever or does it have an end? What governs the motion of the stars that we see in the night sky? And this curiosity about what our ancestors were seeing in the night sky led to the development of science, and in particular astronomy and mathematics, in all societies across the globe. So it didn't happen just in India, it happened in Egypt, it happened in Mesopotamia, it happened in China, etc. And in some sense, astronomy, which is a precursor to cosmology in some sense, but astronomy and cosmology were also perhaps the first applied science, or amongst the first applied sciences. Why? Those days, the societies were agrarian, and you needed to know when to plow the land, when to sow the seed, etc. So you needed a calendar. And what the ancients did was, when the position of a certain star, when a certain star had a certain position in the night sky, they would know that in a month or so, the monsoon will be coming, so it is now time to plow the land and sow the seeds. Or similarly, they would know that the Nile is going to flood, and this is the time that we need to plow the land and sow the seed. So it was extremely important in terms of development of calendars. The second was in navigation. Even 2,000 years ago and more, people were moving across the globe. They were going in caravans across deserts. They were going in ships across the ocean and seas. And they didn't have Google Maps. So how did they navigate? They used the position of the stars in the sky. So they needed to understand very well exactly about where the position of stars would be in the sky and what that meant in terms of direction. I just listed here a large number of people, some people from India who from the 5th century to the 17th century contributed in terms of our understanding of astronomy and mathematics. You have Aryabhatta, Bhaskara, the Varahamihira. Then there was much later the Kerala School of Mathematics and Astronomy. So there were a number of people in India who were contributing to this understanding. But our astronomers, mathematicians were also talking to people in other parts of the world and learning from them, just as their understanding was propagated to other parts of the world. So we benefited from learning from the Romans, while people in China and in Arabia benefited from learning from our understanding. And how did all this information go back and forth? As I said, astronomy was used for navigation by people who were moving from one part of the world to the other. And therefore, when they went and visited another part of the world, they would share with them their understanding of the stars and motion of the planets. And that is how this information moved across the globe. Now, a big sort of paradigm shift and in our understanding, to some extent, of the planets and the stars happened in the 17th century with Galileo and his use of the telescope. He did not invent the telescope, but he used it extensively. He also developed telescopes that gave higher magnification. And the first thing that Galileo realized by looking at the motion of the planets in the sky was that it seemed a far better explanation to say that the sun was at the center and the planets were going around, rather than to say that the earth was at the center and everything else was going around it. Joseph, can you also see me and my hand movements when I'm speaking?
Yes, sir. Yes, we could see you.
So it should be there in the corner of the screen. Yeah. So Galileo comes to this. By the way, before him, Copernicus had also, he's about a century before, or he's in the 16th century. Copernicus has given his model already. But Galileo, with his observations, is able to show argue that maybe a heliocentric model of the universe, of the solar system, is better. By the way, even in ancient times, before Copernicus, in different parts of the world, people had been talking of a heliocentric model of the solar system. Now, Galileo's idea that the sun was at the center and not the earth, disturbed people, because it went against their beliefs that we were special, our earth was special, etc. But then, okay, so let's say that the sun is at the center, but at least we have the moon, because it goes around us. And then Galileo goes and shows with his telescope that Jupiter has actually 4 moons. It has many more, but he could see 4. And the centrality of the earth now completely goes away. We're not at the center of our solar system. We thought we were special because we have a moon going around us, but now we find other planets have even more moons going around them. This not only had scientific implications, but it also had philosophical and religious implications. See, all religions, propose that the gods, prophets, avatars came down to this earth and to make us into better people, better human beings, etc. So in that sense, the earth is also special. If the earth is not special, then does it mean that our understanding of religion, of our gods, prophets, avatars, etc., is a very local understanding, and on other planets, different gods were there, etc.? All of this required people to recalibrate their religious beliefs and made people uncomfortable. And as you know, Galileo actually suffered considerably in his lifetime for his scientific beliefs. A contemporary of Galileo was Kepler. And Kepler used the observations of another astronomer called Tycho Brahe. And on the basis of that, wrote down some empirical laws, which are Kepler's laws of planetary motion. But it is only in later on in the 17th century, Newton gives his law of gravitation, on the basis of which you can derive Kepler's laws. So now you have an understanding of why Kepler's laws might be correct. Please note, the term here, universal. And when we're in school, we're always taught it's the universal law of gravitation. I think it's quite amazing that Newton looked at how objects fall on the earth, got an understanding of the gravity of the earth, and then postulated that this is a law that applies between any two bodies, not just the earth and, let's say, a pen or an apple, but even the sun and the earth, or the sun and other planets. And that is why it is called universal. Based on local observations, it was made into a universal law of attraction between massive objects. The next big change, or the next big leap in our understanding of cosmology, comes when Einstein introduces his theory of gravity, which is called general relativity, and applies that to the universe in the early 20th century. Understanding of the universe. So very quickly, what is the theory of general relativity? First of all, it is a theory of gravity. Just as Newton's theory of gravity is there, this is another theory of gravity developed by Einstein between 1907 and 1950. How do we think of gravity normally in the Newtonian picture? Let's say you have the sun here, and you have a planet like the Earth, and there is an attraction between the two. There's a gravitational force between the two, and because of that, the Earth goes in a orbit around the sun, where the centripetal force is provided by the gravitational force between the Earth and the sun. Now, in Einstein's picture of gravity, it's very different. There is no gravitational force. Einstein instead postulated that if you have the sun, or a very massive object here, its mass, or more precisely its energy density, modifies the space around it, such that if you have another planet moving, if you have another object like a planet moving past it, in this modified space, its motion is such that it goes in an orbit around the sun. So the this motion of the planets going around an object like the sun or a star is not because of a gravitational force, but is because of a modification of space. And that was the basic principle of Einstein's theory of gravity, which is also referred to as general relativity. Now, when this came out, it was an extremely radical idea. Because what do we think of as space? Space is the arena in which all physical phenomena occur. And up till the 20th century, people believed that the matter sitting in space doesn't modify the space. So, we would study Coulomb's law. You take an electron, put another electron, and they repel each other. But this is just a force between the two of them. Their presence in space doesn't modify in any way the space in which they exist. But what Einstein was saying was that no, the presence of the electrons in this space actually modifies the space. Now, and it took some time for people to appreciate it, agree with it, but a number of tests were done of general relativity, and it was found to be correct that, that it does truly supersede Newton's theory of gravity. Now, in school, we teach you Newtonian gravity. Even in first year of college, second year of college, we will teach you gravity. If it is superseded by general relativity, why should we be even talking about Newtonian gravity? Well, the thing is that you need Einstein's theory of general relativity under certain circumstances. For example, when you want to make accurate predictions very close to a massive object. For example, in GPS, when you want to very accurately determine the position of where you are, where your mobile is, using GPS systems, then the calculations that are done to determine your position need to invoke both special relativity and general relativity. Very quickly, how does GPS work? On your phone, well, around the Earth, there are a whole bunch of satellites that are going out. They're part of the GPS system. They're sending out signals. Your phone receives the signals coming from these satellites, and through a process of trilateration, where signals from at least 3 satellites are used, generally more actually, the position of your mobile is determined. Now, where does special relativity, general relativity come in? There are signals going back and forth, and so between the satellite and your phone, and special relativity, general relativity talk of how these signals may be affected by the gravitational field in between, or not the gravitational field, but the distortion of space-time in between. But even more precisely, or to give you an example, what happens is that general relativity predicts that clocks will tick faster or slower depending on where they are in a gravitational field. Now, how far they are from a massive object. So closer to a massive object, clocks may behave in a certain way. When they're further away, they might tick faster. And so you have to adjust the clocks in such a way that this general relativistic effect is taken into account when you're doing the calculation of where your phone is. If you don't do this, if you do not include the general relativistic effects, which modifies the rate at which clocks on the satellite and clocks on your phone are moving forward, or the frequency of those clocks, then what will happen is that in about 15 minutes, your position would be off by about 100 meters, and no Ola cab or Uber cab would be able to find you. So when you want very precise calculations, you need to invoke general relativity. The second is, if you want to study the motion of objects moving close to the speed of light, then once again, you have to invoke general relativity. And finally, when you want to understand the evolution of the universe, you need to invoke general relativity. In all other cases, general relativity reduces to Newtonian gravity to the level of accuracy to which you need to calculate something, and Newtonian gravity works well, and that's why we teach it to you. Okay, so that was a very quick introduction to general relativity. Let's get back to cosmology and the application of general relativity to understanding our universe. So coming back, what is cosmology? It's the study of our universe today, galaxies, clusters, superclusters. How do we do it? We use telescopes and we use satellite-based instruments. Why use satellite-based instruments? Because when you can get out of the, or you can get far away from the surface of the Earth, atmospheric effects that will distort signals coming to our instruments can be minimized. On the other hand, it's very expensive to put telescopes out in space. Also, if anything goes wrong with it, then it's very expensive to fix it. The famous Hubble telescope actually had a problem, and astronauts had to go out into space and fix that Hubble telescope because the mirror had a problem. So when it's ground-based, it's easy to fix. It's a lot cheaper to make and to use. Now, once you have these observations using these instruments, then you can use general relativity, the equations of general relativity, most famously the Einstein's equation, to understand the past history of the universe as well as the future evolution of our universe. So the game in cosmology is that you make observations of the present and then use general relativity to figure out the past or to figure out the future. And these theoretical calculations have to be confirmed with observations. In a sense, this is very similar to what we do in Newtonian mechanics. Given an initial position and an initial velocity, you can use the Newton's laws of motions to say something about the future motion or the future position of the object. Or similarly, if you know the final position and final velocity of some object, you can use Newton's laws of motions to predict from where it came and with what velocity it was released. We play the same game in cosmology. We measure the parameters of the universe today, and then we use Einstein's equations from general relativity to study the past and future of the universe. So if that's what we are doing, then the first thing we need to do is understand the present. And in terms of the present, what I'll talk about today is the structure of our universe today, the dynamics of the universe, and the composition of the universe. And then we'll try and understand more about the past and the future of our universe. See a question mark here for the future, and as I'll mention later on, we are not able to predict completely what the future is going to be like, given our current observation. So what is the present like? You look out into the night sky, you'll see a lot of stars. You'll see stars with planets, just as the sun has planets. You'll see stars in galaxies, like our Milky Way. Galaxies are grouped together in what we call clusters of galaxies. Clusters of galaxies are grouped into superclusters, filaments, walls, with empty spaces in between that are referred to as voids. Now, there's nothing special about the Earth. There's nothing special about the sun either. There are billions of stars like our sun in a galaxy. And just as our sun has planets, other stars also have planets. They're referred to as exoplanets if they're around a star other than the sun. And so far, 6,000 of them have been discovered around other stars. It's very interesting how they're discovered. They're very far away. You can see the star. You generally can't see the planet itself. There are two ways in which they're discovered. Let's say this is the star, and you have a planet going around it. So what you will notice is that the intensity of light coming from this star will be flat, and then it will decrease, and then it will increase again. And that means that something is coming in front of it, and you will see a periodicity to this. And from that, you deduce that maybe there is something going around it, and you can deduce what the mass might be, the speed with which it is going, etc., and determine whether there's a planet over there. The other very interesting technique uses the Doppler shift. Now, we always think of the sun is there, and then the planets are going around it, and the sun is more or less fixed. Actually, the sun is not fixed. Both the planet and the sun are actually moving around the center of mass of the planet-sun system. So while the planet does indeed go like this, the sun itself is also doing something like this. I hope you can see that my fist is moving slightly. Now that is very slight, but our instruments are actually sensitive enough to detect this. And how do we detect it? Through something as simple as the Doppler effect. you know that, when an ambulance is approaching you, the sound from the ambulance, the frequency starts going up. As it's approaching you, as it's moving away from you. That is, the frequency of the sound coming from the source, which is the ambulance, varies depending on the relative motion between the source and the observer. The same thing happens with light. And when its frequency goes down, we call it red shift. When it goes up, we call it blue shift. So because the star is shifting like this, relative to us, we are over here, what happens is that the light from this star, and we know what the typical frequencies should be, some atomic transitions that will be happening in typical stars like our sun, the light will either be, the frequency will go down or it will go up, depending on whether it's coming, moving away from us or moving towards us. And on the basis of that, you can actually discover that if this is wobbling, there must be something else that is going around it that is causing this wobbling. And in 2019, Michael Mayer and Queloz received the Nobel Prize for the discovery of an exoplanet orbiting a solar-type star. There had been an earlier discovery of a exoplanet going around a pulsar, but this was for a solar-type star. Now, in cosmology, why is this study of exoplanets so important? In some sense, the search for another home for the human race has already started. We know that our solar system is going to get destroyed. It'll take a long time. It'll take 5 billion years or maybe 1 billion years. That is, if we don't destroy our planet through wars and through climate change. But at some point, the Earth is not going to survive. And I'll say more about that later. And so we need to find another planet where the human species could survive. Now, there are 6,000, actually, I don't know why it says 5,800. It's about 6,000 that have been discovered so far. But what we're looking for is a planet that has about the same mass as the Earth, because then the gravity on that planet will be similar to that of Earth, which would make it easier for humans to walk and move on that. See, on the moon, the mass is so small that you will be jumping on it. If you had a planet with one small step, you'll actually be jumping up and down because the gravity is very weak there. If you have a planet that has the mass of Jupiter, then if it has a solid surface, then moving on it will be extremely difficult because the gravitational force would be extremely strong. The force of the gravity effects would be extremely strong. Second, the atmosphere that surrounds a planet is a function of the mass of the planet, because on moon, you have no gas there and no oxygen there because the gravitational effects are not strong enough to trap an atmosphere there. The molecules of gases just escape. On the Earth, we have a certain combination of oxygen, nitrogen, etc., because of the gravitational effects of a planet of the size of the Earth. There's another effect that determines the composition of the atmosphere as well as the temperature on a planet, and that is the distance of the planet from the star. If it's too close, then it'll be extremely hot. Things will possibly and life on that would not be possible. If it's very far, then also the composition of the atmosphere and the temperature on that planet would be such that perhaps it would not be possible for humans to live there. So we are searching for an exoplanet that has a mass similar to that of the Earth and is at a distance from the star similar to that of the Earth from the sun, so that the conditions on that planet would be conducive for human life. The search is still on. Of course, the technology to reach such a planet is still not there. It will take a long time before we get there. Well, so much for stars and planets. Stars live in galaxies, and galaxies come in different shapes and sizes. You have spherical, elliptical, spiral, irregular galaxies. This is a picture of a galaxy, which is often called the Milky Way twin. It's a spiral galaxy. The Milky Way is a barred spiral. If we could go outside the Milky Way and could look down on it, or look at it, it would look something like that. if this were the Milky Way, do you know where we sit? So our Earth is actually somewhere over here on the edge of our galaxy. So our sun and the Earth is at the edge of the galaxy. So we are carbon life forms living on a rock that is going around an average star in our galaxy and located at some edge of the galaxy. So there's nothing special about us. And yet, it is very impressive that these carbon life forms sitting in some corner of a galaxy are able to ask and answer questions about the universe as a whole. Now, galaxies are grouped together. One more point I should mention, that the center of most galaxies, you have supermassive black holes. At the center of our Milky Way galaxy, there is a supermassive black hole which has a mass of the order of 4 million times the mass of the sun. A number of people received a Nobel Prize related to showing the existence of black holes and the detection of the black hole at the center of our Milky Way. That was the 2020 Nobel Prize. This is another picture of a galaxy. This is the Andromeda galaxy. It is not the nearest galaxy to the Milky Way, but it is one of the nearest large galaxy to us. Please stare at it very well and look at it very closely. Beautiful that it is. In about 4 billion years, it's going to crash into the Milky Way. We are part of a locally bound system, and it's headed towards us. Galaxies are grouped together in what we call clusters. This is a cluster. All these yellow things that you see here are galaxies. And clusters group together and form what are called superclusters with empty spaces. So these are superclusters or filaments. Sometimes they're like walls with empty spaces in between that we refer to as voids. So that is the structure of our universe as we know it today. Let's then move on to the dynamics. Is the universe static? Has the universe continued looking like this even in earlier times, and will continue to look like this in the future as well? When Einstein came up with his theory of general relativity and applied it to understanding the universe, he presumed that it was. But in 1912, Vesto Slipher, an astronomer, looking at distant galaxies, noticed something, that they were all moving away from us. And in 1929, Hubble and Humason recognized something else, that not only were they moving away from us, they were moving away from us at a speed proportional to their distance from us. And this is known as Hubble's law. And that gave rise to a very interesting conclusion. So Lemaitre in 1927 had also theoretically proposed that something like this should happen. So what they discovered was that, observed, is that all distant galaxies are moving away from us at a speed proportional to their distance. Let's see what this implies. So supposing we are living here on this galaxy, and there are galaxies at a distance of 10 light years, 20 light years, 30 light years away from us. And let's say that they're all moving away from us, as the observations say, and they're moving away from us at a speed that's proportional to their distance from us. So let's say that they're moving away from us at 10 kilometers per hour, 20 kilometers per hour, 30 kilometers per hour. These are not actual astronomical velocities. I'm just using this for an example here. And on this side also, they're moving away at 10, 20 kilometers per hour. Okay, and these are the observations made by an astronomer here. But let's move to this galaxy. And there's an astronomer sitting, and she's also making observations. Now, by just considering relative velocities, what will she say? She will say that our galaxy is moving away from her at a speed of 10 kilometers per hour. This galaxy, which for us was moving away at 10 kilometers per hour, is moving away at 20 kilometers per hour. This is moving away at 30. This is moving away at 10. This is moving away at 20. So she will also conclude that all galaxies are moving away from her. And whichever galaxy you go to in the universe, you will come to that same conclusion as a consequence of Hubble's law. So wherever you are in the universe, what you will say is that distant galaxies are moving away from you. And that is a statement that the universe is expanding. That is, it is not static. And Einstein admitted that he had made an error. So let's understand this concept of an expanding universe a little more. First of all, the question you might ask is that, hey, if the universe is expanding, then why is the solar system staying more or less fixed? Everything should be moving apart. Galaxies, should also be breaking up. Well, these are what we refer to as locally bound system, where the local gravitational effects are stronger than the average gravitational effect of the universe. The average gravitational effect is an expansion, but the local effects are much stronger, and that's why they stay together as bound systems. But distant galaxies, which are far away from us and are not part of, which are not part of a bound system, they are all moving away from each other. Now, things are moving away from each other not because of some intrinsic velocity, like something hit it and it's moving away, because by that count, half of the things should be moving away from us, half of them should be coming towards us. Distant galaxies are moving away from us because space is expanding. These galaxies exist in space, and the space between these galaxies and us is expanding, or the entire space is expanding, carrying matter along with it, carrying the galaxies along with it. You might say, hold it, what is this expanding space? But remember, Einstein's theory of general relativity tells us that space gets affected by the matter that is sitting in it. And if this matter is moving, then, the presence of matter can affect the space. And one of the ways it can affect the space is that the space can become dynamic, and space can also increase between two objects. Can you calculate the rate at which things will be expanding? Yes, Einstein's theory of general relativity does provide that, and it comes through Einstein's equation. And the rate of expansion depends on the average mass or energy density, and the square root of that, in the universe. And it also depends on the composition of the matter. Is it relativistic, non-relativistic, etc.? So the evolution and expansion of the universe depends on the average mass density or energy density in the universe, as well as whether the universe is made up at a particular time of relativistic particles, like in the early universe, or non-relativistic particles at a later time, or something else. So then let's ask the question, what is the universe made up of? So we've looked at the structure. We've understood that the universe is not static. That means it's changing in time because the universe is expanding. But the rate of expansion depends on what the universe is made up of. So let's look at that. Okay. First of all, if you have a detector for radiation, which is electromagnetic radiation, which is photons, and you point it in any direction in the sky away from stars and galaxies, what you will pick up is a background of photons in the microwave. And that is referred to as the cosmic microwave background radiation. This was discovered in the 1960s, and it corresponds to a background of electromagnetic radiation, which in other words is also photons, corresponding to a Planckian distribution at 2.7 degrees Kelvin. And of course, this is all, photons are relativistic. So we're talking relativistic particles in the universe. There's another set of relativistic particles, which we call the cosmic neutrino background, which is made up of neutrinos, which have a mass that's very small, 1 millionth, less than 1 millionth the mass of the electron. And they're produced in nuclear reactions, for example, in the sun all the time, and in nuclear reactors, and they pervade the universe. And this cosmic neutrino background is also left over from neutrinos that were there in the early universe, not just produced in stars. But neutrinos are very hard to detect We can detect them coming from the sun, we can detect them from nuclear reactors, but we have not been able to detect the cosmic neutrino background. So that's relativistic stuff. Now let me talk of non-relativistic matter. This is a picture of a galaxy. It's called the Pinwheel Galaxy. It's a spiral galaxy. And you see a lot of light coming from it. Where is this light coming from? Well, galaxies have stars. What are stars made up of? Hydrogen and helium and certain other gases maybe, but primarily that. And the hydrogen and helium is made up of protons, neutrons, and electrons. And these interact. They have electromagnetic interactions, which produces light. And that's what we detect. So there is luminous matter in all these galaxies. But when people were making measurements of the velocity with which stars at the edge of galaxies were going around and matching their speeds, their velocities, rotational velocity, with what you might expect given the amount of matter that you are seeing at the center of the galaxy, they discovered that there was a huge discrepancy. And what they actually discovered is that there is more matter in this galaxy than what we are observing. That's the only way to explain the speeds with which these, and I'll show you the calculation, the speed with which these stars are going around. Now, this matter is not giving out light, and so we refer to it as dark matter. Now, is this a small problem? I mean, if it's a small percentage of the matter in a galaxy, we might not even worry about it. But it turns out 90% of the galaxy is made up of matter that is non-luminous. That is dark matter. So it is a big effect. It is something we need to know much more about. Now, let me just quickly show you how one came to this conclusion that there was more matter, that there is dark matter in the galaxy. If you take a star, okay, which is going around the center of a galaxy, you know that anything going in a circle, there must be a centripetal force acting towards the center. So the centripetal force mv squared upon r, in this case, will equal the gravitational force of the matter inside the orbit, pulling or attracting this star. Now, you can presume that most of the matter is sitting in what we call the bulge of the galaxy. So as you go to further distances away from the bulge, this capital M, which is the mass in the bulge, doesn't change. Little m here is the mass of the star. R is the distance from the center. G is, of course, gravitational constant. And V is the velocity, the rotational velocity here. Now, this implies that V goes like 1 by square root R. That means if you look at stars at further and further, I hope you can you see my cursor, Joseph?
Sir, we could not see your cursor.
Oh, you can't see my cursor. Oh, I see. Okay,
Yes, yes.
fine. Then anyway, as you move out away from the bulge, the central luminous region, you notice that you would expect that the velocity of these stars should go down like 1 by square root R. As you move away, the velocity, rotational velocity should be decreasing.
Sir,
However,
if you select the pen in the bottom, then you can mark.
okay, I don't want to mark. I just wanted to, let's see if there is a pointer here.
Yes, second one in the bottom.
Okay. Oh, I can use laser pointer. Excellent. Thank you. Okay. So, oops. What I wanted to say is that as you move away at a larger and larger, can you see it now?
Yes, sir.
Yeah, you can see the laser pointer. Okay. So if you move to larger and larger distances, the velocity, rotational velocity of that star should be going down like square root of R. And this is what you would expect, that as you move away from the central bulge, the velocity should be going down. But in galaxy after galaxy, what they noticed is that it doesn't go down. Here it looks like it's going up slightly, but in most part, it is more or less, flat over here. And this doesn't match with our understanding that all the matter is luminous there. So how can it be explained? So supposing we go back to our original equation, mv squared upon r is gmm upon r squared. If I say m of r is equal to ar, then you put it in here, you will get V is constant. But if m of r is equal to a of r, a times r, then as r increases, that means the mass is increasing. That means there is matter outside the central luminous bulge, which we cannot see. And it does not emit light or scatter light. See, you can see an object if it emits light, like the sun, or if it scatters light, like the moon. Whatever is the matter sitting in these galaxies is not emitting or scattering light, and this non-luminous matter is what we call dark matter. Now, this is not a new discovery. The presence or existence of dark matter was discovered in the 1930s. It's over 90 years that we have known that dark matter exists. But what are the particles? What is the substance that makes up the dark matter? We have not yet discovered. You've heard of the Large Hadron Collider at CERN in Geneva, where we have these protons moving at very high speeds in two beams, and then you collide them and you produce new particles. You see, you break up the proton, you see particles inside, but you also, because of the mass energy of the protons or the kinetic energy of these protons gets converted into mass energy of new particles. And so you can create new particles at the collider. The Large Hadron Collider, we hoped would create the dark matter particle, but so far we have not yet been able to. The collider has not created the dark matter particle, or we have not been able to detect it in the collisions there. So as of today, while the presence and existence of dark matter has been seen or is known or inferred from a large number of astrophysical, cosmological observations, the particle that makes it up, we don't know. For luminous matter, I can tell you it is protons, neutrons, electrons. But for dark matter, I don't know the name of the particle that is making it up. Okay, so that's dark matter. There's something else in the universe that we don't know too much about, and that's referred to as dark energy. Now, I told you that the universe is expanding. Observations indicate that the expansion of the universe was decreasing for the first 9 billion years and has been increasing for the last 5 billion years. Universe is about 13.8 billion years old, or 14 billion years old. First 9 billion years, it was expanding, but it was slowing down. Now it has started speeding up. The earlier period of deceleration, slowing down, is understood, but we don't know what is causing this acceleration. It could be explained by modifying Einstein's equations in general relativity. There's something known as the cosmological constant, which you can put in there. Or you say that the universe has some other substance that pervades it. It's a field that pervades the universe and has properties that causes space to expand faster with time. What do I mean by a field? Well, we are familiar with fields on this earth, for example, magnetic fields. And, we know astrophysical systems like galaxies have magnetic fields that exist all through the galaxy. Similarly, there is some new field, and we call it the quintessence field, that exists everywhere in the universe, but it has some special properties that causes space to expand faster with time. Which of these two explanations it is and what is the form of the quintessence field, no one really knows yet. But whatever it is, it's referred to as dark energy. Now, what we have talked about is the composition of our universe. It's made up of background photons and neutrinos. That's the relativistic part. You have the non-relativistic part, luminous, which is protons, neutrons, and electrons. You have dark matter, you have dark energy. I told you that the expansion rate of the universe depends on the composition of the universe, relativistic, non-relativistic, and also upon the average energy density of whatever makes up the universe. So we need to know, is the universe dominated by dark matter, or is it dominated by photons? What is it? And it turns out that at different periods in the history of the universe, different things dominated the universe in terms of its energy density. How do you calculate it? You take any region, you calculate the kinetic energy, potential energy, and mass energy associated with any of these, average it over the volume, and that gives you an idea of what is the average energy density associated with dark energy or protons or photons, etc. Now, today, it turns out that the relativistic material in the universe contributes a negligible amount to the matter or the matter density, energy density of the universe. Protons, neutrons, and electrons, they contribute about, the luminous matter contributes about 5%. Dark matter contributes about 27%. Dark energy, this is contributes about 68%. Look, in a galaxy, the dark matter is concentrated, so it may contribute a lot. But if you average over large region of space, so averaging over the universe, then it contributes 27%. So the universe is today dark energy dominated. Then it is, the dark matter is it's about 27% compared to 68% here. The luminous matter that, what we call baryonic matter that you and I are made up of makes up only 5% of the universe. As I mentioned, in a galaxy, the dark matter may be the dominant, maybe even more dominant than dark energy. But if you average over all the space in the universe, then the dark energy becomes dominant. Okay, so we have done, addressed what the present universe is like. Now, we looked at the structure, the dynamics, the composition. Now let's look at the past and the future. And as I said, the way we do this is by using Einstein's theory of general relativity, where we use Einstein's equations to say something about the past. The questions we would like to ask about the past is, was the universe always like the present? About the future, we want to know, will the universe continue to be like the present? So let's start answering those questions. Let's first talk about the past. So what do we know today? All distant galaxies are moving away from us because their spectra is redshifted. That is, the universe is expanding. That means if you go back in time, so you take any small, take some finite region of space, take all the material that's in there, and you go back in time, the volume is becoming smaller and smaller, which means that the region is becoming denser and denser and denser. As you go back in time, the universe is about 14 billion years old today. At that earliest instant, the density is extremely high. So high, and the energy of particles is also very high. So all the matter breaks down into elementary particles. So as you go back in time, the density increases, the temperature of the universe increases, the energy of particles increases. So you no longer have molecules, then you don't have atoms, they all break up. Atoms break up into protons, neutrons, electrons. The protons and neutrons break up into quarks. You keep going back in time, everything is made up of the elementary particles in nature. And so it's dense, it's extremely energetic, and it's also expanding very fast. Matter is moving out very fast. That initial state of the universe, where things are extremely dense and moving out very fast, is what we refer to as the Big Bang. The Big Bang is that initial state. Extremely high density, extremely high energies, and everything is moving out very fast. Now, there are many misconceptions about the Big Bang, and let me clear up at least one of them. Many people think that the Big Bang is all the matter of the universe is concentrated in a point in space, and it sort of blew up like a firecracker. The Big Bang is not an explosion of concentrated matter in space. It's an explosion of space carrying with it matter. So it's that initial state of rapid expansion of space filled with matter. And so it's just matter and space moving out together rather than matter moving out in space. The term itself is kind of confusing, and incidentally, it was coined by an opponent of the model, someone who didn't quite agree with the model. Okay, so that's the initial state. Right? This initial state of everything moving out, very high energy densities, high energies of particles, things expanding very fast. What happens after that? So in the first second, you have a hot primordial plasma of particles in their sort of most elementary nature. So you have electrons, you have quarks, neutrinos, dark matter particles. At some point, the quarks coalesce in form protons and neutrons. Around the first second and up to about 3 minutes, and a little later than that, the first light nuclei start forming. The hydrogen nucleus, which is the proton, is already there, but protons and neutrons fuse together. They form deuterium, tritium, helium-3, helium-4, lithium, and then it stops. Only then light nuclei are created in this primordial nucleosynthesis. All the heavy elements that make up you and me, carbon, nitrogen, phosphorus, potassium, etc., those are actually created in stars much later, in the nuclear fusion that happens at the core of stars. And in supernovae explosions, etc. So that's happened. This primordial nucleosynthesis happens in the first 3 minutes. Then at about 400,000 years is when the first atoms form. 300 million years, so the universe cools down enough that a proton and an electron can come together and form an atom. Prior to that, they could form it, but some energetic photon would come and break it up. The temperature in the universe, the energy of photons in the universe goes below the ionization energy of hydrogen atom, and that's why atoms can form after about 380,000 years or 400,000 years. 300 million years is when the first stars form. 1 billion in what we call proto-galaxies. Galaxies haven't yet formed. 1 billion years is when the first galaxies form. 9 billion years is when the universe starts accelerating. Incidentally, the solar system also gets formed at that time, but these two events have nothing to do with each other. And 13.8 billion years or 14 billion years is where we are today. Do you notice I have asterisks here? Excuse me, I think someone's microphone is on, if it can be muted. Okay. So that's because the James Webb Telescope is now giving us pictures of stars and galaxies that seem to have formed much earlier than what we had earlier, we had thought in our earlier models of the universe. So maybe the first galaxies are forming around 300 million years. Now, this picture here is not just theoretical. It's based on observations, or predictions are made and then it is confirmed by observations. And that's why Professor Peebles got the Nobel Prize in 2019 for his work on physical cosmology, because he had, as a theorist, had explained things related to nucleosynthesis, the formation of atoms and the cosmic microwave background radiation, galaxy formation, accelerating universe, etc. And these were then confirmed using observations. So these are not just stories, these are based on observations as well. So that was the past. Now, what about the future? The universe could keep expanding, or maybe it won't. So in fact, there are models that the universe expands and then contracts and expands and contracts. And we refer to these as cyclic universe models. For now, let's just think in terms of expanding universe scenarios. Even in that, we don't know whether it will continue to accelerate because of the presence of dark energy, or it will stop at some point. The uncertainty is because we don't know the nature of dark energy. We don't know whether it will continue to dominate the energy density of the universe and the evolution of the universe. Until we have a good understanding of the nature of dark energy, we can't answer that question. So let me just give you 2 scenarios of what might happen in the future. And there are many more. So let's presume the universe keeps expanding. Then in one scenario, all distant galaxies will move away from each other, but the galaxies themselves will retain their structure for a long time, for about 100 trillion years, before the stars will run out of fuel and these galaxies will just turn dark, as in not giving out light. In other scenarios, galaxies move apart, stars in them move apart. Finally, the stars break up and the universe is filled with a dilute gas and becomes dark and cold. And that may take about 50 billion years. We don't need to worry about these scenarios because our solar system is going to get destroyed long before that. The sun is going to heat up as it enters its red giant phase. And in about 1 billion years, the temperature of the sun will be so hot that water on Earth will evaporate and we won't be able to survive. And in about 7.5 billion years, the sun will expand into a red giant whose radius is greater than the orbit of the Earth. So either the Earth gets subsumed in the sun or gets kicked out further. So let me summarize by saying that what do we know of the universe? Well, we live in an expanding universe. The initial condition was a very dense, energetic, fast expanding phase. which we refer to as the Big Bang. Today, what we see around us is a universe made up of stars and galaxies, clusters and voids. And that's what we call the structure of the universe. We also know that the universe is both expanding today and accelerating, but we don't know what is causing this accelerated expansion. And that is why we are unsure about the future, even though we have a fairly good idea about the past. So what are the outstanding issues in cosmology today? One is, why did the Big Bang happen? Or what exactly happened during the Big Bang? The thing is that, when we're going back in time, we're using Einstein's theory of general relativity to understand the evolution, back evolution in some sense. I mean, going back in time. When you go back so far in time, the energy is increased to a point where the energy crosses a certain threshold where actually you need to bring in quantum gravity. You need to bring in quantum effects. Einstein's theory of general relativity is a classical theory of gravity. So technically, it's not applicable at those very early times. And you need a quantum theory of gravity to understand what was happening when the universe was so dense, when energies of particles are so high, and to understand what is happening in the universe at that point. As of today, we don't have a theory of quantum gravity, so we can't really answer this question. You may have heard of things like string theory and loop quantum gravity. Well, they are quantum theories of gravity, but they're not as well formulated today to actually answer these questions. The second is an outstanding issue is what's the nature of dark matter? As I told you, the Large Hadron Collider is looking for dark matter. There are many other experiments looking for dark matter, but we still haven't been able to identify it, the nature of it. And finally, we can't make definitive predictions of the future as parameters related to dark energy have not yet been measured. It is hoped that observations in the near future will tell us more about the nature of dark energy. So these are excellent questions for some of you to also try to address in the years to come. Each one of these is extremely challenging, but I hope that I've been able to pique your interest in these ideas, and maybe someday one of you will be giving a lecture, Professor Satyanarayana memorial lecture, where you talk about an answer to one of these questions. So thank you very much, and I'll just leave you with the last slide, which has a few references that you could look at if you want to learn more about cosmology. There's a book by Steve Weinberg, who's no more, but a famous Nobel laureate, called The First 3 Minutes. Excellent book, except it's outdated, and so it won't talk about dark energy. There's an excellent series of books by G. Venkataraman, who was a scientist at IGCAR, where Professor Satyanarayana was also there. And he has a book, in that series, a book called The Big and the Small. Volume 2 deals with cosmology. And then there are some other references that I've put here. My email ID is over here. You're always welcome to reach out to me. As I said, I'm a professor at Ahmedabad University in Ahmedabad. You can find me on the webpage, and you can always reach out to me in case you have any questions. This talk is also, at least the slides are uploaded on my website, so you can always look it up in case you want to look at something that I may have mentioned today. So thank you very much, and I hope you've enjoyed this talk on cosmology.
Thank you, Professor. I think it is really a very elegant and insightful lecture. Could really understand and follow every slide. When we see cosmology, it looks like kind of big term, but I think you made a really very, very beautiful presentation. So participants, now it is a time for Q&A, question and answer session. So a few questions already posted in the chat box. Of course, the participants who posted, you can directly unmute yourself and you can ask, or otherwise I will read. So first, I think first question is given by Sumit Kumar. Sumit Kumar, are you here? He asked, why are we not able to predict the future but able to predict the past?
So to predict the past, we make use of our observations, and we have a good understanding of the nature of dark matter and the nature of radiation, relativistic particles, and those were dominant in the past. And therefore, we can make statements about what happened in the past. Today, and possibly in the future, dark energy is dominating. And since we don't know certain aspects of the nature of dark energy, we can't make predictions about what will happen in the future. Will this dark energy stay constant? Then I can make a prediction. Will the dark energy increase? I can make a prediction. Will the dark energy density decrease with time? Then also I can make a prediction. But I don't know which one of these three it is. And therefore, I am unable to answer what will happen. I cannot determine what would happen in the future.
I hope you are convinced. So the next question is asked by Lenin Mani, MSc Physics. Sir, if the mass bends time and light, space, then why does not our sun orbit the Alpha Centauri, nearest star of our sun, but orbiting around the massive black hole Sagittarius A star?
No, so these are two separate things. Alpha Centauri is doing it, black holes are doing it. We are not, by the way, so any object which has mass, including you, is affecting the space-time around it. Okay. Now, if we are not very close to Alpha Centauri, then we are not part of a gravitationally bound system, and therefore we are not going to be going around it. There are many heavy objects in the universe or in the galaxy. Unless you have become and formed a gravitationally bound system, you are not going to be, you will not be going in an orbit around it. Just to also clarify that black hole that is sitting in the center is so far away from us that as far as we are concerned, we are not going to fall into it. It just looks like some extremely massive object very far away. That, along with the other stars and gas that make up the central bulge of the universe, of the Milky Way galaxy, is what we are going around. We are in no danger of falling into that black hole.
Okay. So then Jay Prakash Amulraj, so we asked, sir, could you please explain the linkage between entropy and black holes?
So that's a very different question. There are notions of that entropy cannot decrease. It can only increase, stay constant or increase. Now, when things fall into a black hole, we lose information about that object. And so the features of a black hole are basically its mass, its angular momentum, and charge. Whether a car falls in or a donkey falls in, that information is lost when it falls into the black hole, which is known as the information loss paradox. When you want to actually calculate the entropy of a system, you have to calculate the number of degrees of freedom. Now, since you don't know what has gone in, whether a car or a donkey has gone in, you can't actually count the number of degrees of freedom. In fact, more precisely, the number of degrees of freedom or the features of the system that you're looking at are basically just the mass, the charge, and the angular momentum of the black hole, which means that it actually seems to imply that the entropy of the system has decreased when things have fallen into the black hole, which goes against the second law of thermodynamics. And therefore, what people have tried to do is to argue that there are ways in which you can measure certain things around a black hole that might give you information about what has fallen into the black hole, which will allow you to measure more degrees of freedom associated with the black hole, which would allow you to then calculate an entropy associated with the black hole, which can imply that the entropy of the black hole or of the system before and after, the entropy of the system after something fell into the black hole has not decreased. How do you identify that entropy or degrees of freedom associated with the black hole? That is not a fully answered question. Leaving that aside, people have identified that you could if you associate an entropy with the black hole, which is related to the area of a black hole, then you could explain, how the entropy doesn't decrease when things fall into a black hole. But exactly why the entropy of a black hole should be related to its area, that is not, it's postulated, and it looks like if you do that, then something known as black hole thermodynamics works, but the underlying physics, the physics underlying that is not fully understood. And therefore, how you associate entropy with a black hole is not well understood. I mean, we don't exactly understand how one can do that.
So there is one more question from Kiki. So how the universe expansion does exist, like from center or upwards? Something like.
So think of the universe as infinite in size. There's no up, down, top, bottom. It's just infinite space. And the universe just keeps, it's not expanding into something, because the universe by definition is everything. So the easiest way to think of a universe which is expanding is to think of an infinite universe. So it just extends all the way to plus and minus infinity in X, Y, and Z directions. Now you could say, then what does it mean to say the universe has expanded? Well, you have an infinite universe, double its size, 2 times infinity is also infinity. So the infinite volume has just continues to remain infinite. The way you should, now having made that statement, let me tell you the way you ought to really think about it. Don't think of the whole universe and what it's expanding. Think of a finite region of the universe. If this was the region, after some time, it will occupy that much. So if this was the region, after some time, it will occupy this much region. And the region next to it has also expanded. The region next to it has also expanded. And so and that is the way in which you think of an expanding universe. It's not like this expanding has gotten into some other region, that it is pushing in on some other part of space. There's no conservation of space concept. And so the universe, each part of the universe is increasing in size.
Okay. So Ventika Senthil Kumar, yeah. Do the black holes in the center of the galaxy influence the rotation of the galaxy, and also the locally bound galaxies or clusters, sir?
No, they don't. The black hole, as I mentioned earlier, the rotation of the galaxy is a function of how that galaxy got formed. That original gas that was there must have had some angular momentum, or maybe some other galaxy moves past it and imparts angular momentum to a galaxy. It is not related to the black hole at the center. For a whole galaxy, the black hole at the center is a small thing. It doesn't influence things very much, nor does it influence how one galaxy interacts with another galaxy.
I think V. Akash raised his hand. Maybe you can unmute and speak. V. Akash, can ask one question.
Sir, am I audible?
Yeah.
Sir, that's the basic question. So, gravity is a fundamental force. Is gravity?
Okay.
So, why we isn't in standard model particle model? Why isn't see that?
Okay. So there are 4 fundamental forces in nature. There is the weak force that's responsible for nuclear reactions. The strong force that's responsible for example, keeping positively charged quarks together in a proton, because otherwise they would want to repel each other. So then there's the electromagnetic force that we are familiar with, and there is gravity. The standard model of particle physics combines the weak force, the strong force, and electromagnetic force, but it does not include gravity. So gravity is not part of that. We want a theory that would combine the weak, strong, and electromagnetic and gravity, and string theory in principle would do that. And it is a quantum theory of gravity, but we still don't have a good theory that works.
Okay, sir. And one more question, sir.
Sure.
Can black hole explode like a Big Bang singularity did?
Not, we don't know. I mean, the Big Bang was as I told you, is a very different kind. It's not an explosion of matter, right? Matter was just sitting there and the space expanded. The black hole is something else. It's a lot of matter that has concentrated in a particular position. And I don't think there are any concepts of black holes exploding. There is a concept of black hole evaporation. So very small black holes can give out radiation. Larger ones will give, but you'll never notice it. But small ones may give out. And so in principle, the black hole may lose a lot of mass that way. But what is the final stage of that evaporation? We don't know, because we don't have a quantum theory of gravity. That evaporation gives rise to something called as Hawking radiation. But what will be the final state of that evaporation? No one knows, because we once again need a quantum theory of gravity. And Einstein gravity will not work there.
Then what causes the point to explode in the Big Bang theory, sir?
That's what I said. No, that is an initial condition of the universe. Okay. So we observe the universe is expanding. So if you go back in time, it has been expanding for all. Now there are models of the universe called cyclic universe, in which the universe is contracting, regions of space become smaller, and then it starts expanding, and then it starts contracting, then it starts expanding. So the Big Bang for us in those models is that it comes after a contraction, and then the universe starts expanding again. But exactly what caused all of that, no one knows, because the quantum theory of gravity that could explain it doesn't exist yet.
Okay, thank you.
Yeah.
Nikanda, you can ask.
Good evening, sir. Sir, our observation is limited by the age of Earth. I mean, if something exists before the age of Earth, can we observe those stars or galaxies, or there is a limitation?
Oh, no. Many things that we observe have been around. So like the oldest star that we have seen, let's say something is 100 million years after the Big Bang. Now the oldest galaxy that we see is 300 million years after the Big Bang, or let's say 1 billion years after the Big Bang, while the solar system was formed 9 billion years after the Big Bang. So we are seeing things that were created billions of years before the Earth was created. But they are so far away that the light has reached us only now. So when you see a very distant object, not only are you seeing something very far away, but you're also seeing something that existed at a much earlier time. That's not how it looks today. Because it has taken 13 billion years for that light to reach us. So the signal is that of something from very long ago.
But sir, if something is 8 billion years ago, that light will never reach us, right? Our Earth is just only 5 billion years old.
No, it
right?
will reach us. Supposing we are over here, something happened over here. Something we didn't exist. Some explosion happened here. The light is coming, light is coming, light is coming. After this explosion happened, let's say the solar system got created. But this light has not yet reached us, and finally it reaches us. So what we are seeing is a signal from something that happened over here a long time ago.
Okay, sir. Sir, one more question, sir. You have said this galaxies move away. They are related by this Hubble's law. Their velocity is proportional to the distance they are apart. So that means there is an acceleration which causes this galaxies or universe to expand. What is the origin of that?
No, so
What is the-
right now, the acceleration of the universe today is because of something called dark energy, and we don't know what makes it up. So how the universe is evolving, accelerating, decelerating, depends on what is there in the universe at that time, okay, which is the dominant thing. So the early universe was dominated by relativistic particles. So the universe was expanding, but if you're dominated by relativistic particles, you will slow down. So it's decelerating. At some point, dark matter becomes more dominant than the relativistic matter in the universe. So if you take the average energy density, there is more dark matter than photons in the universe. At that point, again, the universe is expanding, but it is decelerating. So dark matter also has the property that it will make things slow down. About 5 billion years ago, what happened is that the dark matter energy density decreased, the dark energy density became more than that of dark matter. Because these things don't stay static, they decrease, they change in time. Now, the dark energy has some property that makes the universe accelerate. But what are the properties of dark energy? We don't know yet.
Thank you.
Yeah, I think this is the last question from Alfina.
Okay.
Sir, what is inside the black holes? And black holes is the key door of another universe. Black hole absorbs everything, even light cannot escape. So where are these things?
So how do black holes form? Okay, if you have a very massive star, regular star, but very massive, then the gravitational force is strong enough, the gravity is strong enough that this thing collapses. That things called the pressure that could have prevented a collapse is too small to prevent the collapse, and it collapses. And all this matter goes to a point. Now you can ask, where did that matter go? I mean, forget about things falling into the black hole. That stuff that was made up, that original star itself, where did it go? At one level, I can say it's all sitting at that point. But the correct answer is that when all of this matter becomes concentrated, the density is so high that your general relativity is no longer working. And you need a quantum theory of gravity to explain what is happening to that collapsed matter that is all getting concentrated, most likely not at a point, but in some small finite region. Very, very small finite region. But the density there is so high that only quantum gravity can tell you what happened, what is going on in that region. And then quantum gravity will explain to you that if something else falls into the black hole, what happens to it? Of course, it will break up and all that, but in what form and in what nature is it sitting at the center of the black hole? And so the answer to your question will have to wait, because we do not have a quantum theory of gravity that can explain it. There are black holes all over the place. There's nothing very special about them. Only if you get very close to it will you get trapped. Even light will get trapped and fall in. But if you're a little away from it, nothing. It will just look like a very massive star and you can go past it.
Okay, sir. So I think one more question came from Shanmugapriyan.
Yeah.
Quantum fluctuations are thought to have played a critical role in the early universe.
Yes.
Can you comment on this?
Okay. So if you look at the structure of the universe, you see stars and galaxies and stuff like that. It's very non-uniform, right? It's not smooth. Now, what we believe, so how does this structure form? The idea is that, that the early universe was not also smooth. It was fairly smooth, but there was in some regions, there was a little more matter. Some regions, there's a little less matter. Some regions, a little more matter. Some regions, a little less matter. Later on in the history of the universe, when what happened is that regions where there was more matter started accumulating through gravity matter from the surrounding regions, and these regions grew, their mass density grew, their mass grew, and finally they collapsed and formed galaxies. And the regions that were underdense got even more underdense, and they became emptier, and they became voids, etc. So this is our understanding of how structure formed in the universe, how galaxies, empty spaces, etc. formed in the universe. The question one will then ask is, how did you get this initial fluctuation of perturbations in the distribution of matter in the universe? And that is supposed to come from quantum fluctuations in the matter fields that existed in the very early universe. Those fields don't exist today. They have decayed into whatever the matter that we see today. But because there were some fluctuations in those fields, they gave rise to fluctuations in the distribution of matter in the early universe, so that in the later part of the universe, when structure formation happened, these fluctuations or these perturbations grew and collapsed and formed galaxies and clusters, etc.
Fine, sir. So yeah, actually, yeah, one more question from my side. So recently, our Jayant Narlikar passed away.
Yes.
So yes, actually, so he's one of the very important pioneering in this field. So
Yeah.
usually people say that his idea of the universe, formation of universe, is still unconventional. So what way it is different? So can you comment on this?
Sure. So many years ago, when all the data was not available, Hoyle, Narlikar, Burbridge, etc., created a model of the universe which was static. But over a period of time, people discovered that no, there's more and more compelling evidence that the universe is not static, it is expanding. And so they modified their theories and came up with something called so theirs was called steady state cosmology. Then they modified it to call it quasi-steady state cosmology. They had to postulate certain things in the universe that would compensate or could explain the observations that we see today, because we do see many things are dynamic and changing in the universe. By and large, the feeling in the community is that the quasi-steady state cosmology model does not quite work, given the large number of observations that seem to indicate that what we call Big Bang cosmology is the correct one. But I have to say that Professor Narlikar and his collaborators, in their efforts to explain, to make quasi-steady state cosmology compatible with the observations, came up with some brilliant ideas, which may or may not have worked for quasi-state cosmology, but other astronomers use those ideas to explain other phenomena that they see in the universe. So their contribution has been immense. I mean, one should always question whatever is the reigning paradigm, and I appreciate that he did it. But even beyond that, some of his explanations were used in to explain other phenomena in the universe. And so there has been a great contribution of Professor Narlikar, Hoyle, Burbridge, etc., in our understanding of the universe.
Nice, sir. So if a MSc student wants to pursue his research in this cosmology, so what your advice or what is your inputs to them?
Sure. Great. The first thing is you need to study everything in MSc: classical mechanics, quantum mechanics, statistical mechanics, mathematical physics, electricity and magnetism very well, because these are the underpinnings of all theories in physics. Then at some point, it may happen in your MSc or it will happen during your PhD. You will have to take a course in general relativity. Some universities offer it at MSc, fine, you should take it. But if your university doesn't offer it, don't worry. When you go to do your PhD at some place, they will give you a course in general relativity. Once you have mastered, as in studied general relativity, as part of that course, you will also understand how general relativity is applied to understanding the universe. There's something known as the Friedman-Robertson-Walker metric that you will read about, which is the basic ideas related to the evolution and structure of the universe. Beyond that, you will have to read papers during your PhD, which will teach you more about the structure and evolution of the universe. Alongside, now in cosmology, there are two sort of kinds of cosmologists. There are those who look at the observations, they're the experimental cosmologists who are making the observations by designing experiments, detectors, either ground-based or satellite-based, and then analyzing the data. Then there are others who are looking at the large-scale structure of the universe, looking at the data and making conclusions about the evolution of the universe. And then there are what are known as particle cosmologists, like myself. We actually study the early universe. Now, if you're studying the early universe, that's, as I have been mentioning, it's very energetic, etc. So the particles of the universe are the elementary particles of the universe, and you'll have to understand how they interact with each other. So you have to study particle physics, because it's not just electromagnetic interactions. Now you have to study weak force, strong force, the standard model of particle physics, possibly grand unified theories of particle physics, to understand how these particles interacted with themselves, with each other at high energies in the early universe. Now, that was then. We are here today. So what do people like me do? We make predictions as to these things interacted with each other in the early universe. This was the end product of those reactions. These are those particles that will continue to exist and survive till today, and they will be behaving like this today. And then we make some prediction as to what you will see today as a remnants of the early universe physics. And then the observers go and make those observations and come back and tell us, yes, it agrees with the theory, or no, it doesn't agree with your theory. So this is the sort of things that happen in cosmology. There's experimental work happening. There is physical cosmology work happening, which is where you use the data from experiments to try and say something about how the structure of the universe is today and how it is evolving. And then there are particle cosmologists who try and go back in time and try to understand what was the structure, what were the particles in the universe in those early times, and how they would, what you can predict about the universe today. All of this requires a fair amount of study, which usually happens at the PhD level. At most, you will get introduced to general relativity and cosmology in a course at the master's level. But if you don't worry, you will learn that and much, much more at the PhD.
Thank you, sir. Thank you. Really, very nice sessions. Now, I think, yeah. So I invite Dr. Tirsenthil to propose vote of thanks.
Hello? Just a minute. Sir, am I audible?
Yes,
Yes.
yes.
Sir, we are extremely thankful to the presentation that you have provided, Professor Raghavan Rangarajan, who opened a PRL and presently at the Ahmedabad University. Professor started with explaining earlier observations about the universe with the Galileo telescopes and other works which was done before the Galileo's time. And he really started out with explaining the origin of the universe and how the elements were created. And he went on to explain the origin of the discovery of dark matter through galaxy rotational curves, etc. And he provided a valuable guidance to the youngsters to enter into the cosmology. And we are very much thankful to you, sir. And by the name of Satya sir's memory, and you are also a friend of him. So I hope that all the students are benefited from that. And I am also thanking all the participants of the program and making this Satya sir's memorial lecture series continuously as a successful one. And we hope that we will keep remembering the Satya sirs by means of making this kind of discussions or lectures in the later time also. And I am also thanking to Joseph Prabhakar, Kamal sir, and all the organizers of the event. And I hope that all the students have benefited. Thank you, sir. Thank you very much. And thank you everybody who participated in this program through Google Meet and also through the YouTube. And the video will be available forever in the YouTube channel. So students will also get benefited. And also it's a very good introduction of you to the participants. And I hope someone will contact you in the futures to get more clarifications. Thank you, sir. Thank you.
Thank you, sir. It's a really
Thank
great sessions. Thank you, Professor.
Thank you so much for giving me this opportunity, and I really appreciated the questions that also came. So thanks to all of you for being part of this today.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.